Okay, and we're recording right now. Okay, so the goal of today is to focus on graphing motion. We've already talked about ways to analyze motion mathematically, so calculating velocity and calculating acceleration. But today we're going to focus on graphing. In fact, we're going to spend the next 2 days on graphing motion. Of course, I posted a YouTube video for you guys to watch on Edpuzzle last class period to kind of introduce position time graphs, which we're going to kind of go in more detail today. And then hopefully by the end of this class period, we'll be ready to start velocity time graphs. And then when I see you guys next Tuesday, we're going to go into even more detail with position time graphs and velocity time graphs. Okay, so we're focusing on graphs for today. Now, before I pull up a PowerPoint presentation, let me show you guys something. Okay. I'm going to be honest with you guys. I was very reluctant to teach this lesson of a graphing. So there was some hesitation. There was some reserve for me. And the reason why is because typically in the past, whenever I teach graphing, one of the things that I would do, I would have my students, on that particular day, whenever we're working on this assignment, I would have my students go out to the football field, and we would collect data of the motion of 3 volunteers, and then after that we will come back to the room and we will plot out their data. And I typically like presenting graphs that way because it allows you as the student to get real world examples of how graphs look like plotted from actual data, from real world data. Now, obviously, I can't do that this year because we're in the middle of a pandemic, and you guys are not at the school right now, so we can't go to the football field. But what I want to do now, I just briefly want to tell you guys what we would do in the past. So I will get 3 volunteers, or 3 main volunteers. I will get someone to be a runner, someone to be a walker, and someone to walk the field in the opposite direction. So in other words, let us assume this is the football field, and somewhere around here, let's just say this is the 0-yard line. So if this is the 0-yard line, all the way over here is the ideal 100-yard line, right? Because the football field is 100 yards. So basically, my walker would start from here and walk all the way to this end of the field. The same thing with my runner. My runner would start here and run all the way to this end of the field. And then I would have someone who would play the role of my walker in the opposite direction, where they would start here and then they would walk toward this end of the field. In other words, they will walk from the 100-yard line to the 0, assuming this is our reference point here. This is 0. Everyone else who was not one of my 3 main volunteers, they would stand on the sideline here with their stopwatch in hand. So basically, they would use the stopwatch on their cell phones to collect time data. Okay, and then we will come back to the classroom and we will put the data in an Excel spreadsheet. And guys, here is an example of data taken from my 8th period class last year. Okay, so my 8th period class, this is the data that we took. And again, so we see we had a walker, we had a runner, and someone who walked the field in the opposite direction. And then we had some with the 5-yard line, 10-yard line, 15-yard line, 20-yard line, and so on. And so then we would collect data. And then when we plot out the data, this is what we get. Okay. So here's an example of, and by the way, assuming we're plotting position along the y-axis and time along the x-axis. Now, when you plot out the data, you're not going to always get a nice smooth line. And the reason why, because there's going to obviously be human error in the data. So what we do, we draw what is known as a best fit line through the data. And the best fit line looks something like this. Okay, so here is how the graph looks like for my walker. And here is how the graph looks like for my runner whenever we plot out the data and we look at the slope. Can someone tell me What is the main difference between the slope of my walker and the slope of my runner? Anyway, what do you notice about the slope between the two? Because this is very important for position time graphs. So, does everyone see that the runner has a steeper slope compared to the walker? So, guys, remember that. That's very, 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 very important. On position time graphs, if you have a straight sloping line, the steeper the slope, the faster the person is traveling. So both these objects are moving at a constant velocity, but the person with the steeper slope is moving faster. Okay. Here, this line in blue here represents the walker who walked in the opposite direction. So, in other words, he started at the 100-yard line and walked toward the 0-yard line. And I want you guys to notice here how this looks like. For someone who's walking in the opposite direction, we actually get a negative slope. So this is definitely a negative slope here. So keep that in mind. For objects on a position time graph that are moving in the positive direction, they have a positive slope. And for objects that's moving in the negative direction, they have a negative slope. Okay. So that's just something I want you guys to keep in mind. Now, with that said, let us look at the PowerPoint for graphing motion. Now, again, guys, since we are not able to go to the football field and collect our own data, in this PowerPoint here, I'm just going to go over the basic trends that you get from graphs. And of course, after going over those great basic trends, hopefully you guys will be able to do the 2 assignments that I'm going to post tonight or later on today. And of course, the PowerPoint is going to be available to you guys or for you guys so that you can use the PowerPoint to assist you on the assignment. And of course, whenever we do our 6 weeks test, one of the benefits of you guys testing from home is that you are allowed to use the PowerPoints and any notes from class on the test as well. So, okay, be sure you go over that. Okay, so now, guys, so even though we have here a distance time graph, note that in some of the assignments that I give you guys, you're going to see this labeled here a position time graph. If you see that, know they mean the same thing. Distance time graph is the same thing as a position time graph. They follow the exact same trends. So we always plot time along the x-axis. Okay. And position or distance gets plotted along the vertical axis. Okay, so I'm saying it again, time gets plotted along the x-axis, which is in other words the horizontal axis. And then distance gets plotted along the vertical axis. Okay, that's always true for our position versus time graphs or distance versus time graphs. Okay, now, here's the first thing I want you guys to understand here. If something is not moving on a distance time graph, the way you know that object is not moving, if you look at that graph and you see a horizontal line, if it's a perfectly horizontal line, this by definition means the person is not moving. And this makes sense, right? Because what this is saying is, as time progresses, this person literally stays at the same position. Their position does not change. So that means an object that is at rest must have a horizontal line. Okay? So this is for an object that is stationary. It's something you guys need to keep in mind. Okay. And we just said this, an object that is moving at a constant speed, if you plot out the motion on a position time graph, you get something like this. You get a straight horizontal line. I'm sorry, not a straight horizontal line, but you get a straight sloping line. a straight sloping line with no curves, and this indicates the object is moving at a constant velocity, or in other words, a constant speed. I'm going to say something here, guys, just to give you guys a little preview of something. Okay. If this right here represents an object moving at a constant speed, how would something look like that's accelerating? So, again, I'm getting a little ahead of myself, but this is a perfect point here because I want you guys to see the difference between an object that's moving at a constant velocity and an object that's accelerating or speeding up, because we're going to see more of this next class period. Okay. So, for an object that's moving for an object that's accelerating, you will have something like this, a curved line on a position versus time graph or distance versus time graph. So notice the line that I drew in yellow. That's a curved line. This line represents an object that's accelerating. So it's specifically speeding up while moving in the positive direction. The blue line represents an object that's moving at a constant velocity. So it's a straight sloping line, whereas the curved line represents an object that's accelerating. So that's just something I want you guys to keep in mind. Okay. Now, I talked about this about 10 minutes ago. I'm going to repeat what I just said. If you have two objects and you compare the slopes of those two objects, basically the object that has the steeper slope is moving with a greater velocity. So clearly this object in yellow here is moving faster than the object in blue, because this object is has a steeper slope. Mind you, they both are moving at a constant speed. They're moving at a constant speed, but one clearly is moving faster than the other. Okay. So right here, they prove that to you guys, that one is moving faster than the other, by actually calculating the slope of the line. Guys, remember, what is slope? Slope is rise over run. So guys, look at the yellow line here. For this yellow line here, notice that our rise, in other words, along the vertical axis here, we went a total of 30 meters. Okay, so our rise is 30 meters, and our run here is 10 seconds. As you can see, right, from here to here is 10 seconds. So we want a rise of 30 meters, and we want a run of 10 seconds. So rise over run in this case gives us 30 meters divided by 10 seconds. In other words, 30 meters per second represents the magnitude of our velocity. Okay. And my lights just went out. So, I'm sorry, not 30 meters per second, but 3 meters per second represents the magnitude of our velocity, because if you do 30 divided by 10, you get 3 meters per second. Now, guys, look at the line in blue. So, if we do rise over run, so here we rise 20 meters, and we run 20 seconds. So 20 meters divided by 20 seconds gives me 1 meter per second. So clearly, guys, when we do our mathematical calculation, the yellow line has a speed of 3 meters per second, and the blue line has a speed of 1 meter per second. So clearly the yellow line is moving faster. Guys, remember this, how to calculate slopes, because on your assignment that I will post tonight, or later on in the day, you will have to do computations with slopes on a position time graph. Okay. Now, what is happening here if we look here at this object on a distance time graph, or in other words, a position time graph? So what this is saying is that the object is moving at a constant velocity here. And as soon as it gets to this point right here, it rapidly speeds up. And then from this point out, it just moves at a constant velocity again. So now in the real world, you wouldn't have a graph like this where, you would have this jump here. It would be sort of like a tiny curve there to represent speeding up. But the point is that I want you guys to know is that here our object is moving at a constant velocity at a relatively slow speed. and then here it's moving at a constant velocity at a relative high speed. So just something that I want you guys to keep in mind. Okay, so it's moving slow, and then it's moving fast. So if you see a distance time graph that looks something like this, that's what that means. Okay. We already talked about this right here. If you see a distance time graph that looks something like this, where the line is curved, this basically means the object is continuously accelerating. So it's not moving at a constant velocity at all. It is continuously accelerating throughout the course of its entire trip. In other words, it's speeding up. It's going faster over time. And to be specific, this object here is speeding up in the positive direction. Okay, so what's going on here? So what's going on here at interval A, and then time interval B, and then time interval C? Okay, well, this is actually pretty easy here. During interval A, so we're moving at a constant velocity at a relative slow speed, okay? And then the object comes to a stop, and it comes to a stop for a few seconds, okay? So it comes to a stop for a few seconds, and then it moves at a constant velocity, but it moves at a constant velocity here at a relatively high speed. Okay, so everybody got that slow velocity at a constant speed, comes to a stop for a few seconds, and it moves at a constant velocity at a relative high speed. Okay, let's keep going. Okay, what's going on here? So we see an object moving at a constant velocity at a relative high speed. Then it moves at a constant velocity at a relative slow speed. And we know that because this slope here in light blue is not as steep as the slope in dark blue. And then from here to here, the object changes direction. So it starts moving in the negative direction. So for these two time intervals, it's moving in a positive direction because we see a positive slope. And then here, we're moving in the negative direction. Okay. Now, the question is here, how do we calculate these slopes? Okay. So let's go ahead and do that right now. So let's do the math. Let me see. So if you look at stage one says basically, and then stage one represents the line in dark blue here, that the object moves 100 meters in 10 seconds. So the rise is 100 and the run is 10. And when we do rise over run, 100 divided by 10, that gives us 10 meters per second. So that's our velocity for stage one. What about stage two? Here, from this distance to this distance represents 50 meters, right? Because 150 minus 100 is 50. So here we go 50 meters in 10 seconds. So rise over run, 50 divided by 10 gives me 5 meters per second. So that's the velocity for stage two. And then stage three, in order to calculate this velocity, here we went 150 meters in 20 seconds. 150 divided by 20, that's 7.5 meters per second. But of course here, this is a negative slope, so we have to write the number. We have to make the number negative. So again, we see this 10 meters per second, 5 meters per second, and 7.5 meters per second. But to be specific, this is supposed to be a negative here. So whoever made this PowerPoint, they should have put a negative there because that is a... Oh, well, you know what? Since they're only concerned with speed and not with direction, that's why they put 7.5. But just know if this was velocity that you were finding, that would be a negative velocity. Okay? So this is just something that I just said. The slope indicates the rate of change of position. So the slope of the line is steepness tells you whether or not it's going fast, slow, whenever you're comparing that object to other objects. So the slope gives you an idea of speed. I'm going to keep repeating that point because that's a very important point. Okay. This was something that I said earlier. A curved line indicates an accelerating object. The object is changing its speed. Okay, so just repeating what I already said earlier. If the slope appears to go uphill, this means the object is moving in the positive direction. If the slope appears to go downhill, this means the object is moving in the negative direction. Okay. And just remember something that I already said. Anytime you see a distance versus time graph, know that means the same thing as a position versus time graph. Distance time graphs and position time graphs are the same thing. Those terms are used interchangeably in this course, specifically when we're talking about graphing. Okay. And that is the end of the PowerPoint. Before we complete this class period for the day, I want to briefly introduce to you guys velocity time graphs as far as comparing them to position time graphs, because we will talk more about this on the next class period. So let me get ready to pull this up in Kami so that I can annotate it. No, that's wrong. Document. Okay, let me find the right document here. I did not want this to save. Hold on, guys. Before I share my screen, let me erase this stuff because it's saved and I didn't want it to. I have to erase these annotations. Okay. So give me just a second. I'm pulling up a file on my phone because I'm using this file for this PDF, for these blank graphs in this PDF that we're going to be looking at. Okay, now, guys, in physics, there are three major types of graphs that we deal with. We deal with position time graphs or distance time graphs. We also deal with what is known as velocity time graphs, and we also deal with what is known as acceleration time graphs. Now, I'm going to be honest with you guys. Between now and next week, I don't think I'm going to have enough time to cover acceleration time graphs, but for sure we have to cover position time graphs and velocity time graphs because position time graphs and velocity time graphs are the most important in this course. Um, um, acceleration time graphs, they're pretty easy, but again, like I said, I don't know if we're going to have time to get to those because, we're on a very tight schedule. We have to get so much done by the end of the 6 weeks period. So we will be focusing on position versus time graph and velocity versus time graphs over the course of the next 2 days. Okay. I want to begin here by saying something here. Okay, so guys, according to everything that we just went over, if I have a position time graph and my line looks something like this. Okay. Someone tell me, anytime you see a position time graph and you see a straight sloping line like that, what does that mean about our object on a position time graph? What's happening to this specific object I just drew, guys? Well, could someone unmute themselves and tell me what direction is this object traveling in? Is it traveling in the positive direction or the negative direction?
Negative.
Exactly. It's traveling in the negative direction. You knew that because it had a negative slope. And so As it's traveling in the negative direction, it is moving at a constant velocity. So I'm going to say something, guys. Whenever you're taking this exact same situation and you're drawing it on what is known as a velocity time graph, you would draw it something like this. You would go down here to the negative end, right? Because these are all positive velocities, and here at the bottom of the graph is all negative velocity. So you would come down to the negative end, and you would draw a straight horizontal line like this, and make that line as straight as possible. And so this exact same scenario right here on a velocity time graph looks like this. So notice our velocity is constant. Now, assuming this velocity was constant at 5 meters per second, then I would come here and I would draw a straight line through 5 meters per second. And notice the velocity stays constant with time. So this is this exact same scenario represented on a velocity time graph. What about this right here, guys? What about this situation right here? Let take a look at this situation in red. Okay. What exactly does this mean? If I have a straight horizontal line on a position time graph, how would I draw this exact same scenario on a velocity versus time graph? Well, guys, think about what this means. Remember what I just said. Anytime we have a horizontal line on a velocity time graph, this means our object is at rest. And that makes sense. I'm sorry, not a velocity time graph, on a position time graph. Anytime we have a straight horizontal line on a position time graph, that means our object is at rest. And that's because what's happening here is that our object is basically staying at the same position as time progresses. So if it's staying at the same position as time progresses, it must not be moving, right? It's not changing its position. It's just sitting there. So, guys, something that's at rest that is not moving, by definition, has zero velocity. So, guys, whenever you're drawing this exact same scenario on a velocity time graph, you always want to come here to where you see zero velocity, and you always want to draw the line through the 0 point. Okay. So that indicates so this right here on a position time graph looks like this on a velocity time graph. Okay, so that's exactly what that means. That we have zero velocity, so your velocity time graph must go through 0. Let's do a few more examples before we're done. Okay, so in here I want to compare two lines here. So we have one line that looks like this in purple, and we have one line that looks like this in green. Okay, guys, which one of those objects is moving faster than the other object? The line in purple or the line in green?
Purple.
Yes, the line in purple, because it has a steeper slope. It has a steeper slope. Now, guys, how would I represent this exact same scenario on a velocity time graph? So they're both moving at a constant velocity, but the line in purple is clearly moving faster because it has a steeper slope. So that means, guys, if I was to replicate this exact same scenario on a velocity time graph, I better be sure that I make my purple line higher than my green line, right? And notice they both have positive velocities, right? Because remember, on a velocity time graph, you're going to always have a positive end and a negative end. They both have positive velocities because they both have positive slopes. But on a velocity time graph, they're straight horizontal lines because the velocity stays constant, and the purple line has to be higher because it's moving at a greater speed. And of course, I didn't actually calculate these slopes here. I just, gave a hypothetical scenario, assuming this was moving at 8 meters per second, this was moving at 4 meters per second. But the point is that the purple line is higher than the green line because it's moving at a greater speed. So remember that, guys, whenever you're comparing two objects on a velocity time graph, the line that is higher is moving at a greater speed compared to the line that is lower on the graph. When you're looking at the positive end. Of course, on the position time graph, the line that is steeper has greater velocity than the line that is not so steep. Okay. One more scenario. Suppose I wanted to represent something like this, guys. Suppose I wanted to represent something like this. So here I have an object that is continuously accelerating on a position time graph. Notice because I have a curved line there. So since I have a curved line there and we are continuously accelerating, how would I draw this on a velocity versus time graph? And by the way, this is something we're going to talk more about in detail next class period. I just want to introduce this to you guys right now. But if I was to draw this exact same scenario on a velocity time graph, it would look something like this. So notice how as time increases, the velocity increases over time. So notice we're speeding up, we're accelerating, we're continuously speeding up. Okay, guys, so we're going to stop here. I'm going to put the link to the attendance form in the chat box. Again, for anyone that did not get it. So please fill it out. If you did not fill that out at the beginning of class, remember your project is due tomorrow. It must be turned into Schoology. And it must be, of course, I'm going to post an assignment, and then you guys have to attach your PowerPoint presentation or a picture of your poster board to that assignment in Schoology. It is officially due tomorrow, but you are allowed to get it to me Sunday night before midnight if you choose to, if you would like that extra time. If there are no questions, you all are free to go, and I hope you all have a good day. Bye.